everyone. I'm Zahra, the moderator for today's session. Welcome to the October AI Community Talk. Thank you for joining us today. We are delighted to have here for what promises to be an insightful and engaging session. This event is organized by the AI-driven Sri Lanka 2024, which is an initiative of the IEEE Young Professionals Sri Lanka in collaboration with the IEEE Student Branch of SLTC. Today, we will explore a crucial topic in AI, face tracking in challenging illumination. So, without further ado, it's my great pleasure to introduce our esteemed guest speaker for today. We are honored to have Dr. Rajitha Navaratna, Principal Data Scientist at OCTAVE John Keells Holdings. Dr. Navaratna has graciously joined us today to share insights into face tracking techniques and the latest practice in the field. Please join me in welcoming Dr. Rajitha Navaratna. Over to you, sir.
Thank you, sir. Let me share my screen as well. Hope you can see my screen.
Yes, sir.
Thank you. Okay. Okay, cool. Let's start. Thanks for the introduction, sir, and myself. I'm Rajitha. So I'm currently heading the data science discipline at Octave and working as a principal data scientist. And in profession, I'm a computer scientist as well. And so what I'm trying to discuss today is to go through another area of artificial intelligence, especially in the visual domain. Okay, and when you are talking about the intelligence as a human, we have several intelligence skill sets. So we have naturalistic intelligence, where as a human, we have the ability to understand and recognize objects. So we have the ability to recognize, okay, this is a tree, right? This is a toy, or this is an animal. So we do have that intelligence, and so this intelligence came from maybe some of the inputs that your parents provided you in the beginning, or maybe you just learn by yourself in the beginning of your life cycle, right? So typically, people take around 20 years to develop some of this intelligence. But if you look at the life cycle of a small child, so around first 1 to 6 years, that's a good rapid growth. So you are learning analytic intelligence and the intrapersonal intelligence, right? Where you have the ability to understand emotions, whether someone is laughing or crying, or whether someone is surprised. You also have intelligence where you hug people, you can kiss people, right? Some of those type of intelligence, musical intelligence, right? Everyone love music, everyone, right? And you have that intelligence, and also you do have some of this logistic intelligence. Right? This linguistic intelligence is easy to learn, especially when you are in the early stages of your life cycle, especially 0 to 6 years. So that will allow you to learn language, and also the small kids, they pick up the words very quickly. And also once you go up to the age 12, so that's another development stage where people are, have at least achieved around more than 70 to 80% of this intelligence, and then it started to have a slow growth, right? So this little bit of about the human intelligence, but artificial intelligence, currently trend, what we are trying to do is, in a very basic terminologies, we try to mimic this intelligence, right, using a computer. So we try to mimic this human intelligence. right? So today what we are trying to discuss is the visual aspects of this intelligence, and also one particular problem in visual domain, right? Where we need to understand, or in this case, the computer should be able to understand whether we can identify a person or not in a very challenging lighting conditions. Let's say maybe in a very dark lighting condition. So human does have that intelligence, right? So you are developed in such a way that with experience, so you can identify humans' emotions even when someone is smiling in a very dark lighting conditions. Obviously, there may be a little bit of challenges, but in overall, it has a good amount of intelligence. So what we'll try to do is to understand this visual domain, right? So when you talk about this visual domain, right, maybe you might have seen some of these movies like Avatar, right, where they try to use actors, right, and they train in a very controlled environments, right. They try to track their facial expressions and their movements, right. So you have as you can see in the right hand side, so you have a camera in front of you, so it's capture your all the emotions and also all the landmarks, especially the very interesting landmarks. And typical computer scientists use different landmarks marks. Like typically people use 68 landmarks, but there are very dense level of tracking also available, especially when you need very tiny details, and even especially for movies, right? So you do have these type of technologies, and movies do use a lot of these experiments. So prior to I joined with the John Keells Holdings, I worked with the Walt Disney Imagineering in United States. From 2012, we worked with the movies, right? We work with the TV shows. Right? So yeah, we do a lot of experiments to understand these human behaviors, especially in the movies, and also comedies and dramas, right? And how we resonate these facial informations, how we can identify these facial expressions, right? In a control environment and also in a very challenging environments using computers. Okay. So if you look at these visual domains, right? So the visual information is basically it's a bunch of numbers. It's pretty much right. So you have call these pixel values, right? If you have like a 32 by 32 image in a very nice way, you have 964 pixel values, right? So these pixel values, this information is transformed into different formats using different technologies to understand either emotions or maybe their activities, right, the landmarks, all of those things. But if you look at the nutshell, it's basically a vector, right? In this case 964 into vector. So how can we use this vector to understand some of these intelligence that people has the ability to identify, right? So this is one of the intelligence that a lot of scientists are working on, and also we have succeeded in several business domains as well, where people have using these type of technologies, especially movie industry, right, dramas, even cartoons, right, and now in these days like self-driving cars also, they're looking into how we can utilize face tracking and face registration, especially in the drivings, right? But the challenge is, if you look at this left hand side, so this is a person who are driving a car where the lighting is changing, right? It's not a constant lighting when you are driving a car, right? You might just think about that. You start to drive a car even during the morning, you might can see, when you go from different roads, the lighting is changing, right? So how an intelligent system can track this facial expression and also the face registration throughout that the journey? It's a challenging task in artificial intelligence too. So if you look at this understanding this human behavior, right? So what is try to do is it has two major components that I can highlight. And one is try to analyze and recognize of motion patterns. Right, so it has some motion patterns when you smile, laugh, there are some motions are happening, and it's also involve actions and interactions between, among, or objects. And so this the understanding of the human being, right? So these facial expressions and the body gesture are the most research or most richest informations elements that human has, right? So the facial expressions and also your body movements, when you are talking, even in a meeting, right? So you realize you are using your hands a lot, right? Maybe to convey some messages, right? And even myself now, I'm doing that. So your facial expression and body gestures, so you have a lot of rich amount of information. So the ability to recognize human behaviors through vision is essential for enabling intelligent machines human interactions, right? So that's why it's really important, and facial expressions and body gestures have a big part to play in this journey, right? So if you look at this face, right? So face has a lot of informations such as expressions, and also we as a human beings, we do have the intelligence to understand humans. As I mentioned, one is the different lighting conditions, also different scaling, right? Maybe if you think about it, that you are in a stage, right? And performing something, let's say you're a musician, right? And you have audience, right? So you have the ability to understand, or at least recognize the people in front seats, and maybe up to some certain level of the back seats too. So, but however, the scale factor is, you can see the scale is changing, right? You don't have the same scale factor compared to the front seats and the back seats. But as a human beings, you do have that intelligence, right? And also we do have that intelligence where if there is an occlusion, right, we can tend to take a call. Okay, this person is, let's say, Amit, or whoever it is, right? You do have that intelligence as well. The second option is, you do also have the intelligence to understand pose, right? Whether I might be, in this case, frontal view, but maybe if I'm looking at in another view, I might be in a angle of, let's say in this case 90 degrees, or in this case maybe 60 degrees. But we as a human beings, we have that understanding as, but typically we don't think this type of intelligence, it's naturally comes, right? I think with the development of our life cycle, these type of intelligence are there. But when you are going to come up with intelligence system, artificial intelligence systems, these things are challenging, right? So in this talk, what I'm just going to highlight, it is only one particular challenge where we call this illumination condition, and how we do when we are having a lighting changes, and maybe
I didn't get that. Could you try again?
Yeah, so just only one intelligent, and then a proposed system that we can looking into implement this type of intelligence, right? So what I'm looking into is the illumination. So there are different techniques we do looking into the pose, right? Or we can identify people in different poses, right? So you can have a people in front view, then you can have let's say right hand 30 degrees, maybe 90 degrees, 60 degrees, left hand 30 degrees, 60 degrees, 90 degrees, right? But as a humans, we can understand the who is that particular person is. Maybe sometimes we have that ability to recognize some of these emotions into some extent. Yep. Good. Any questions? If you have any questions, please drop it in here. So I'll try to go as slow as much as I can, because in the later part, there's a little bit of mathematics come into play. I just also wanted to highlight the field of mathematics is playing a huge role in artificial intelligence, right? So if you are looking for an AI engineering career, right, field of mathematics is definitely one of the probably essential field. It's a lot of intelligence are derived from fundamental of mathematics. And so I will highlight few mathematical concepts as well along the presentation, so you can just take a notes and go and check it out in your leisure time as well. Yeah, cool. If you have any questions, just ping me. So let's go through this phase alignment, right? So if you look at a particular phase, let's say in this case, so this is a very controlled setup. So this is in a research lab in United States, right, in Pittsburgh. So so this research and the experiments that we have running is actually in a controlled setting, right, in a very controlled setting, and the lightings and the cameras are pretty much fixed, and we are instructing to the audience, in this case, we also sometimes call subjects, or we sometimes call samples, right? Different instructions, right? So you need to laugh, or you need to anger, you need to express different expressions, and also we are capturing this behavior from different angles as well, right? So we have front camera. So in this case, what I'm showing is a front camera, but you do have cameras from different angles, right? So to capture a good amount of view, and you do have a 24 cameras, and also we have 7 lighting conditions. So we do change the lightings also, so as to understand how the lightings can affect for these AI systems, right? Just for a so if you look at this phase, right, so you might have seen this type of registrations, right? One is, you might can see this boxes type of registrations, right? So if you look at your phone, or maybe even your camera, nowadays, these things are popping in, right? We call these course type of registrations, right? So we try to understand the most important informations, and could be eyes, nose, mouth, and typically you have this bounding box, in your piece, right? And the second one is where this fine registration, like the movie like Avatar, they use very fine registration. So in this case, what I'm showing is with the 68-point tracking. So you can see some of these corners, it's a point, right? All of these corners are point, and it has 68 points, and also you have X coordinate and also Y coordinate, right? So if a particular point in here, you have X coordinate. So let's think about this as a 2D domain. So you have X coordinate, and also you have Y coordinate respect to a 0, 0, right? And so if you look at that particular information, so if you have 68 points, so you have 68 into 2 metric, right? 68 into 2 metric. So each particular point represent a maybe nose point, or maybe here, maybe mouth corner, like that. And each particular point has 2 components, X and Y. So that's why you have 68 into 2, that will be 138.6. So you can convert this metric into a vector as well. So if you have 68 by 2 vector, if you convert it into vector, that will be 136 into 1 vector. All right. So in these domains, we typically talk about the matrices. We have talked about the vectors as well. So I'm just trying to highlight some of these things. It's essential, some of these mathematical concepts, and also you do needs to understand the derivatives, right? Vector derivatives. So it's a little bit of different matrix derivatives, how we can do the derivatives, like some depth level of pure mathematics as well. Yeah. So cool. So, but in generally, like, these are the 2 levels. We have the fine registrations. We are trying to understand all of these points, and also the course type of registrations. So if you look at some of these examples, right? So what you are seeing is, so you have some points, right? So you can see the red point is a point, right? So if you look at this particular point, right, as X and Y coordinates, the thing is you have to manually label these things. So someone has to manually label. Okay? So someone has to train these systems. So someone has to tell, these are the points, and these are steps, and these are the 3 points here, 4 points here. So you need to manually label, especially if you have like a video, you need to manually label these things in your keyframes. For example, if you are recording a video for 30 frames per second, right? So you need to understand where the key frames, where the changes are starting to happen. Right? Maybe I might stay neutral for a while, then maybe started to smile, right? So where you need to understand where the keyframes, and then you take the keyframes, and then you need to label it, right? So here you need a human inputs, otherwise the system, right? It's going to train, so might provide different outputs, right? So here we are training these AI systems. So okay, these are the points. Okay. So if you look at this particular picture, I'm just only showing a one particular lighting condition, right? So very good control lighting conditions, right? There's no lighting changes of a particular person, and we are asking him to change different emotions, and we are taking some profile photos from a one camera from frontal view. Yeah. Cool. So here are a few examples, like different people, and if you look at this, one of the registration image, you should be able to understand. One is there is the shape. If you take it out the picture in this case, right, you should be ended up with a nice shape. We have something like the eyebrows, two eyebrows, eyes, and nose here, and then maybe something like this. It's just the shape. So the second component is you also will identify there's the appearance. So you have the color, you have the appearance changes of a particular subject as well. Okay, so that is also there. If you look at one particular image, okay, so you have two components. One is the shape. The second one is, we call this appearance, right? So when you are developing these algorithms or intelligent systems, or in this case, the face tracking systems, right? You can do two ways. One is you can come up with a very generic model. It's a very generic model that's can work for everyone, right? The second option is you can have a specific model where it's only working for you, right? If you look at iPhones, right, they have this face tracking systems, right? When you have a iPhone, they ask you to do different things, right? And they try to register, right? What they try to do is they try to understand your landmarks from different directions, right? And create a particular model, but that is only working for you. So we call this type of model person-specific models. So it's only working for you. Even if you look at this Avatar movie that I showed in early, so she has a front camera in front of actor, right? So they will generate the avatars only for that. If you don't mind, can you go on mute? Thank you. So it's only working for you. Yeah. And the other one is called this generic models. So you try to model it for maybe you can do it for a group of people, right? Or maybe particular company, right? You wanted to open the doors, right? You can do a generic model as well, or you can do even person-specific models. But in this case, if you have a person-specific model, if you have 100 employees, you have 100 models. In generic model, 100 you have only one model. Yeah. But there are different challenges, with the generic models as well. We'll dig deeper to do more into the person-specific models, right? So you are creating a model for only for yourself. So here are a few things, right? And if you look at this person-specific models and the generic models, so I didn't mention about this concept of AAMs. So we call this active appearance model. So we call this active appearance model. So we have the shape variation and the appearance variations, right? So initially I just mentioned about the image, but we call this active appearance model, right? Which has shape and the appearance, right? So from here onwards, I'm going to use the word AAMs. Cool. So if you look at the person-specific aims and the generic aims, so as I mentioned, person-specific models are the most successful method currently, you can see in practice, right? In movies or even in the iPhones and the some of the security things, right? So this person-specific active mapping models are the most successful method, and they have very high registration performance because it's only training for yourself. And it has the ability to understand different expressions, And one question is the labeling, right? So the labeling is there, but for the generic active appearance models also have the labeling, but you can do it only for one time and then use that particular model for all the people, right? But however, the registration is very poor, the performance, right? Compared to a generic and person specific, generic active appearance models are very poor in terms of the registrations, right? So from here onwards, I've got a little bit of maths popping in, right? So if you let's go back to this person specific active appearance models. I'm just talking about the shape component, right? If you look at this shape components, as I mentioned, you have X coordinate and Y coordinate, and the V is the number of vertices. In this case, it could be 68 or it could be 1000, or it's based on how fine details that you need, right? And this particular vector can be represented from x1 to y1 to xv to yv, right? So that's where the V is the number of vertices, right? So if you look at these things, there are some challenges will pop in, right? So we need to do this analysis called progressive analysis, right? So this training measures, or we call this measures, or shapes, needs to be aligned, right? So one technique that we call this progressive analysis, right? And we also use principal component analysis. We'll use to build a 2D linear model of this shape variation, right? So this is the shape. So we can represent this shape S, right, with a mean plus some components. Okay. So the PI is, we call this some parameters, right? SI is the different shapes. Okay. And also the second component is we do have this appearance component, right? Your texture component. Okay, texture part. Okay. So these appearances also have different appearance as well for the different labeling images that we had during the training time period, right? So you are labeling different images with a different appearance, right? So you have only the appearance. So just think about it just for here, right? So where the appearance is, you might have these type of images. The shape, you might have these type of images, right? And so this appearance and the shape both can be represented as a mean appearance, or mean vector plus principal component analytics parameters, right? So you can have a some parameter in the shape. For the lambda, we use the lambda. For the shape, we use the p, and some of these measures from the appearance and also from the shape as well, right? So you can go up to a particular variance that you want. Okay. So this is kind of how we do represent these images. So once we have this, now a little bit of the maths going to be complicated, right? So we have the shape and this appearance informations, right? And what we are trying to do is we wanted to use the concept called this warping, right? So the warping actually it refers to the process transforming this visual information. So in this case, we have the texture, we have the color, whatever the intensity value, of a particular given image, right? And you need to fit it into a particular shape, right? So you have, in this case, we have this shape, right? And bottom you have the shape. So let me put it in here. So you have this shape component, right? And also you have this appearance component. So I'm just going to warp it to appearance to this particular shape. So you will end up with this. So what we wanted to understand is, right, how are we going to fitting in these type of images, right? So initially you might have some shape, right, and appearance, right? I wanted to fit it in. right? So initially, we are not going to get the right level of information correctly, right? So we will start from somewhere, maybe here, right? Then step by step, it needs to generate, right? So maybe I'll just go through a very quick video just for you to highlight. Just so here, oops. So you can see initially it started from somewhere, and then slowly, step by step, it started to fit it in, right, to the correct shape, right? So it started step by step. So that's what we try to do, right? I mean, this is a very slow version of this, but typically these things are, very good synchronicities. Okay, so that's slide of the underneath. So what we try to do, find is, assume we have an image. Our goal is to minimize that particular error. Right. So initially we have here, I want to fit it in. So I want to minimize that error. Right. And so the way that we are going to minimize is using these shape parameters and the appearance parameters. So those are the two important things. So we have this here, appearance that we represented a lambda 0, right? And also the shape, right? So here also you can see that those things are given in here. Right? So I'm going to go into the mathematics, all of those things behind, right? So the top equation can be represented as the bottom equation, where you are introducing a matrix Q, right, which is an identity matrix, right, where you have a diagonal matrix which has only one. Yeah. So you can try it out how we can get it in. I'll tell you maybe some mathematical what do you call these principles for you to follow. But for the time being, just think about that, the bottom equation is given for you, right? So initially you have some points, right? When you have initially points, I'm going to fit it in, right, and try to get the minimize, right? So the question in here is, so these things are not linear relationships, right? So between a shape and the appearance parameter. So it's very difficult to solve this objective function using linear relationship. So I need to convert these things into a linear relationship in a such a way my appearance parameters also have a step-by-step improvements. My shape parameters also have step-by-step improvements, right? So that equation can be represented into the given equation using concept called Taylor series. Right? So again, go and check it out. Some of these concepts, how we can represent a given particular function using Taylor series, fx. Right? So we have fx. How can I represent this information using Taylor series? Right? So now a little bit of mathematics come to play. So we can represent this information using Taylor series. So in case, then we can change this appearance and also the shape parameters as a linear relationship, as a linear. Right? So the lambda will be appearance will change step by step in a linear. Yeah. So here's a visual example. Right? So you have collected some training labels, as I mentioned, it's in the very fixed lighting conditions, right? And so initially you might see something like this, right? So I'm just going to fit a particular model for this particular image, right? So initially I'm just starting from here. I just need to step by step, fit it in. So I tried 3 iteration. It start 1 iteration, then go to another iteration, try to update my parameters, my shape parameters and appearance panel, check there. Then again, use that, update it, and check it out where it is. Then you go to the another iteration, right? Step by step, we started to iterate. So in this case, initially we had a good amount of error. Now, when you come to the 10th, 15th, 20th iteration, you might can see that it started to fit it in. So that's what that video showed. But in this case, you can see this the training images initially that I label are in the same lighting condition, and also I'm testing with the same lighting condition. Yeah. So the problem will start popping in if I train something in a nice lighting condition, and then if I started to test it out with a different lighting conditions. And so it will, so then the challenges will start to pop in. right? Where the models doesn't have that information about the lighting variance, because I train in a very good lighting and then I'm trying to test it out something in a very dark lighting, right? So if you look at in this case, these models doesn't have the lighting, doesn't have the ability to understand, also control the lightings. Yeah. So that's where the challenge started popping in, especially with the fine registrations, right? In this case here. So if you look at some of these, the outcomes, I'm just showing one example. So if you have the match condition means, so your training images and also the testing images are in the same, right? So training video and the testing video in the same lighting condition, right? So you can see it's converging very well, right? After some time, it started to fit it in, right? But if you have mismatch conditions, right? Your training images in a one illumination and the testing in a second illumination condition, it started to diverge, right? So the current challenges. So one of the key output in here is this registration active appearance models they are very sensitive to the lighting conditions. They are very sensitive to the lighting condition. But if you look at some of the applications in real world applications, you might not have that opportunity to, have this application in the same lighting conditions. So you may have to deal with it, different lighting conditions, and we'll see how we can deal with it, one algorithm. Okay. So if you look at that phase tracking in dynamic settings, so here are few possible solutions, right? One solution that I can see is, why not we try to manually label different, landmarks in a different lighting condition for the same particular subject. Well, let's say me, so I have some, landmarks, right? I just go and manually image it. I go to another different lighting condition, I can do that. So I take those images also to my training process, right? Go to another lighting condition, I can do that. So that's one way of solving this particular problem, right? But obviously that you can see that is, very time consuming, and also there are some constraints also there, right? How do we decide, how many lighting conditions I should go, right? The second information is understand whether we can encode some of these illumination variations. And can I encode something, right? We call this in this using some filters, right? So if you look at this encoding factors, right? Can I pre-process the image, right? Maybe using some filterings. Like if you look at this human vision, it's very sensitive to understand these reflections, right? So here's an example of showing a Gabo filters, right? So you have different scales and also different filters as well. And we as a human beings, we just, response to these local changes, right? Yeah, Gabo filters that is widely, using in these domains. Okay, so can we take that image and filter it out using these filters? So the image will go through these filters to understand these local changes, right? Rather than just taking the raw image, right? So what I'm looking into is, how can I look into this particular problem using Gabo features instead of using this manual labeling. Like you can do the manual labeling as well, but it's very costly, right? And also it's unpractical as well for different situations, right? So what I'm going to try to do is just take the initial model fitting algorithm, and I wanted to bring it in where the images will go through filters. So now in this case, we have scale filters and also the what do you call the frequency as well. So let's assume that we have 8 scales and 9 orientations. So you have 72 filters. Okay. So I'm trying to send these images through those filters, right? In this case 72, but now it's computation, it's very expensive, right? Compared to the traditional one. Okay. So if you look at this, right, what we are trying to do is, so now it's going to the signal processing concepts. So you have 2 signals, right? Now I'm going to, use this convolution matrices. Convolution. I'm have one objective function. I'm going through this using a filters, and I'm going to convolute, right? So So this is the new objective function, right? Which I want to do it and understand this shape and the appearance parameters, but it's very difficult to do the convolution in a spatial domain, right? So we are going to buy some of these concepts from signal processing, where we can convert the concept of convolution into a dot product in a Fourier domain, right? So where we can represent these convolution concepts as a dot product, right? But now you can see there was a matrix S start to popping in instead of Q, where the S is the filter responses for that particular image. Right? So S can be, you can derive where this will be, sigma into M is the number of filters, in this case 72, right? And you can identify this matrix, and you can plug it in to this equation. Okay. But these images are in the Fourier domain. Okay. And this Fourier domain information also again can be transferred into using these Fourier vectors, right? And convert into original equation, where our matrix Q earlier, it was an identity matrix, right? If you look at the bottom equation, right? And also the earlier equation that we had. In this case, let me go back. Here, right? The top equation, you can see only the difference is the Q matrix, right? But in the same lighting conditions, the Q is actually I, which is the identity matrix, right? But now this matrix changed to Q, right? It's changed to Q, where Q is represent the Fourier basis vectors plus the diagonal of the filter responses. Yes. So if you can calculate only this S metric, so it will be same equation, where instead of I'm using Q equal 1, I'm now using Q equal F transpose S into F. F is the Fourier basis vectors, right? So these are two algorithms, right? So initial one, we call this Euclidean active appearance model. The one that we derive, we call this Gabor Fourier active appearance model. We use Gabor features to encode different variation, and also we use the convolution, and we transform into the Fourier domain. So we are trying to wrap those wordings. I'm just represent as Gabor active appearance model. So you can see the both equations are same except the Q metric. Okay. Good. So let's look at some of these experiments, and you can see when the lightings are matched and both algorithms started to work in, and when the lightings are different, only the Fourier active appearance model, where it started to respond for different local changes, started to converge, right? But you can see, there's a little bit of a higher error compared to mismatch lighting conditions. Okay. So here's an example. It's an early example that I showed you, right? So when the lightings are same, both are started to fit it in, and you can see this Gabor Fourier active appearance model started a little bit late, right? The computation is a little bit expensive, right? And so I'll just skip this outcome. But when the illumination conditions are mismatched, right? So you are training in one lighting and testing in the different lighting conditions. My algorithm or Euclidean algorithm is not going to converge, and you can see the Gabor active appearance model started to converge because it started to respond to these local changes using Gabor filters. Okay, it's worked for even for the different expressions as well without any challenges. Okay. So if you look at this in a video sequence, right? So this is testing that we did it in lab setting, right? I'm asking a subject to do different expressions in a one lighting condition and change the lighting condition. The moment you start the change the lighting conditions, you can see this Euclidean active appearance model is started to diverge, and it's never going to come back. And Gabor Fourier active appearance model, it started to respond and was able to track your face, throughout that video sequence. Right. So here's like some of these outcomes just to check it out, like how far we are from the labeled points, right? We will check the Euclidean distance. So that's why it says the Euclidean appearance model. And you can see that when the informations are match, right? Both algorithms work very well, and the lightings are changed. So the above fully active application started to perform well. So it's an example in a driving scenario, right? In this case, I'm just asking, sorry, the subject is reading something. So this is not the driver at this case, right? So you can see the moment the lighting started to change in the Euclidean active appearance model started to diverge from the points. Yeah. So still there are some challenges that the scientists are working on, how we can get very, very dense level of registrations in the different lighting condition, different occlusions, right? When the pose changes, right? So these are some of these challenges, and also what the AI engineers are working for this understanding this interpersonal intelligence. Okay, so here's just an example. This is another example in a park that someone is walking. So so that's what I just wanted to highlight today, to understand how we can use the visual information for face tracking, and also some of these challenges, right? We have post challenges, illumination challenges, occlusion challenges, scale challenges, and only highlighting one particular challenge, how we can track this face registration, especially the fine registration, using Gabo Fourier active appearance model, and also want to touch base some mathematics to demonstrate the importance of the mathematics in these AI systems, right? So as a developer, it's not only that we want to understand these tools and the frameworks, but it's really important that you understand what is the underneath algorithms, and also the underneath mathematics behind it, right? So then you know where to go and change it, right? With special different ideas, right? So just look at some of these key takeaways, right? So the recognizing human behaviors through vision is very crucial, right? As I mentioned, and obviously there are some difficulties as well, pose, occlusion, lightings, right? And this human vision is very sensitive, and we do have that intelligence. The question is how we can bring that intelligence to the computers, so then they also can understand and respond to these difficulties, especially post, occlusion, lightings, and scale impact. So those are a few key takeaways in terms of the subjects. I also wanted to highlight, make sure you read some of these mathematical concepts, and also the vectors, matrices, the derivatives of vectors, integral of vectors, those type of concepts also try to implement that as well. And that's pretty much it, what I want to highlight. If you have any questions, feel free to connect with me through my email address as well. And I will definitely respond to those emails. And yeah, if you have any questions, I'm happy to take. Yeah, over to you, sir. Any
Thank you
questions?
so much, Dr. Rajitha, for that insightful session. I'm sure everyone has learned a lot. Now it's time for our Q&A session. If you have any questions, please drop them into the chat or unmute your mic and ask.
Yes, one is asking, is the easy way to create a image identification model very easily for a beginner, right? So initially, maybe you try to use some of these tools available through some of these frameworks, where you can test it out and especially this start with the course level of registration rather than the fine level of registrations, especially the algorithms like other boost, right? Is try to understand the registration and also use different filter responses as well. Right? So that's something that you can test it out. And some of these models, sorry, libraries like dlib, right? It has these capabilities for you to test it out, right? And check whether the fine registrations are good enough. And also there are some parameters it's providing to you for you to change, right? And obviously OpenCV has some computer vision libraries for you to use it. That might can be a good starting point as well. I can understand that the mathematics is a little bit, making the life. But it's important for you to understand these concepts. Right? Go and check it out, some of these concepts, especially when you are moving in the industry. It's always important not only to understand the tools but also understand the underneath of mathematics. That will allow you to get highlighted in the community. Okay, sir. If you have any direct questions, please email me. I'm happy to answer. Thank you.
And thank you all for those questions. And thank you, Dr. Rajitha and Navaratna, for the thoughtful answers. And we would like to take this moment to express our gratitude with a virtual token of appreciation for your time and expertise. Thank you once again, Dr. Navaratna, for your invaluable insights and for broadening our knowledge in the field of AI. Thank you all for joining us for this valuable session. And before we wrap up, let's take a snapshot to capture this moment. If you are comfortable, please turn on your cameras and we will take a group photo of AI community talk attendees. All right, with a countdown of 3, let's take a picture. I'll give you a moment to get ready. 3, 2, 1, and we will capture the moment. Everyone smile. Perfect. Thank you so much, everyone. And with that, we conclude this month's AI community talk. Special thanks to today's participants. We truly appreciate each of you for being here and making this event a success. Once again, a special thanks to Dr. Navaratna for sharing this invaluable insight with us. We hope to see you all at our next community talk. Until then, take care and have a wonderful evening.
Thank you.